Yeah.
Okay, so we'll be starting another few minutes. Why people from theory one group itself are not present? Akshat, are you here? Or Aruna?
Yeah, bro, I'm here.
Why people from theory one are not here?
Attack them. Let's see how many.
Okay, it's time. So you can start, guys.
Okay, so am I audible?
Yes.
So hello everyone, this is 31 cohort and I am Siddharth Atila. And so we have so far studied about the life of stars and now we will be discussing about the death of a star by supernova, in particular the type 2 supernova. The next slide please. Okay, so supernova occurs for the stars of mass greater than 8 solar masses, but not about more than 50 solar masses. And if it's above 50 solar masses, then it will directly convert to black hole without any supernova. So a type 2 supernova results from a rapid collapse and violent explosion of a massive star. And now we'll discuss this in detail. So unlike the sun, massive stars, about 8 times massive than sun, possess the mass needed to fuse elements that have an atomic mass greater than the hydrogen and helium. The degeneracy pressure of electrons and the energy generated by these fusion reactions are sufficient to counter the force of gravity and prevent the star from collapsing, as we all know, and maintaining the stellar equilibrium, so-called hydrostatic equilibrium. As a star this massive evolves, it undergoes repeated stages where fusion in core stops and the core collapses until the pressure and temperature are sufficient to begin the next stage of fusion, reigniting to halt collapse. And these onion layers are formed as shown in this diagram. And the star is converted into a red giant. Okay. So here we can see that in this diagram, initially the helium is formed and there is some hydrogen left. And you might think why there is some hydrogen left, because it might be because of that, as the mass of a star is not exactly the 8 times the solar masses, it might be greater. So the helium fusion starts before the all the hydrogen in the star is used to make helium. Okay. So the factor limiting this process in the amount is the amount of energy that is released through fusion, which is dependent on the binding energy of this element. In addition, from carbon burning onwards, energy loss by neutrino production becomes significant, leading to higher rate of reaction that would otherwise take place. And this thing will be discussed by Meghna later in detail. This thing, the fusion thing continues until the nickel 56 is produced, which decays radioactively into cobalt 56 and then iron 56 over the course of only a few months. As iron and nickel have the highest binding energy per nucleon, the energy cannot be produced at the core by fusion, and nickel iron core grows. This core is under huge gravitational pressure. Yeah, can you please play that video, Meghna? So it's just to have your attention towards the screen. It's not quite relative here. So when the compacted mass of the inner core exceeds the Chandrasekhar limit of about 1.4 solar masses, electron degeneration is no longer sufficient to counter the gravitational compression. Then a cataclysmic implosion of the core takes place within seconds, Without the support of now imploded inner core, the outer core collapses inwards under gravity and reaches a velocity of up to 23% of speed of light. And the sudden compression increases the temperature of the inner core to up to 100 billion kelvins. Neutrons and neutrinos are formed via reverse beta decay, releasing about 10 to the power 46 joules in about 10-second burst. Also, the collapse of the inner core is halted by neutron degeneration, causing the implosion to rebound and bounce outwards. The energy of this expanding shock wave is sufficient to disrupt the overlying stellar material and accelerate it to escape velocity, forming a supernova explosion. The types of these will be discussed by my friends later. The shock wave and extremely high temperature and pressure rapidly dissipate, but are present for long enough time to allow for a brief period during which the production of heavier elements, heavier than the iron, can occur. Depending on the initial mass of the star, the remnants of the core form a neutron star or a black hole. Yeah, if it is less than about 3 solar masses, it remains a neutron star. But if this star's weight is more than about 3 solar masses, and this limit is the so-called Oppenheimer-Volkoff limit, then it collapses further to form a black hole. Now, the 4 types of supernova will be discussed by my friends. Thank you.
Guys, is my PPT visible? Can any of them can tell me?
Yeah.
Yeah. My name is Simran, and actually, I'm gonna explain about the 2 types of supernova: supernova type 2N and supernova type 2B. First, let's talk about the type 2N supernova. Can anyone just explain what happens in type 2N supernova? Guys, am I audible?
Yeah, you are audible. We cannot, you can.
Yeah, if I'm audible, then you can answer me, right? Am I audible?
Yeah, Simran, you can start slideshow, I think.
Okay. First, let's talk about type 2N supernova. In type 2N supernova, type N means denotes narrow, which means narrow intermediate width line of hydrogen emission lines are present in their spectra. And then the ejecta from the supernova will interact with the gas around the star to form circumstellar medium. The estimated circumstellar medium which has high observational properties, has high intensity than expected, which can be calculated from the stages of stellar evolution theory. And then this high density was due to the high mass loss of type 2N progenitors. And then this high mass loss may be higher than 10 to the power minus 3 solar masses per year. They actually originate as stars, which can be very similar to luminous blue variables before explosion. And then the examples of type 2N supernova are SN 1998S and then SN 2005 GL, and the energetic supernova can be SN 2006 GY. And now let me show you the picture of one of the type 2N supernovae. Guys, this is a picture of Supernovae 2006 GY. The kinetic energy which was produced by supernovae ejecta was more than sufficient to drive the light curves which can be seen in supernovae circumstellar medium. The circumstellar medium was a way convert into kinetic energy into electromagnetic radiation, which can be observed by a distant person. And then the speed of supernovae ejecta can be 10 to the power 3 and between 10 to the power 3 and 10 to the power 4 kilometer per second. And then the surface where the supernova ejecta and then circumstellar medium meet is known as contact discontinuity. This contact discontinuity actually obeys conservation of mass, where the conservation of mass means the rate of mass flowing in can be equal to the rate of mass flowing out. Hey guys, now let's discuss about type 2b supernovae. In type 2b supernovae, the weak hydrogen lines are actually present in the initial spectrum. And then as hydrogen becomes undetectable, as we have talked that the hydrogen lines are very weak, then the second peak in the light curve becomes very much similar to the type 1b supernovae light curves. As discussed by Aruna yesterday, most of the outer layers will be expelled from the supernovae then due to the loss of hydrogen in the core collapse. And this can happen due to the interaction with the binary companion star in a binary star system. And then if this ejecta expands more, the hydrogen layers become more transparent, and then it will reveal its inner deeper layers. And then this type 2b supernovae was introduced by Ousley in 1987. It can be closely applied to SN 1987K and SN 1993J. And then its very famous examples of type 2 supernovae are then SN 1993J and then Cassiopeia A. Now let's talk about the Cassiopeia A. Cassiopeia A is the youngest supernova remnant in the Milky Way. And then it was observed by most of the astronomers in the night sky between radio waves and gamma rays. And then the discovery of light echoes around the supernovae was actually detected due to the scattering and then absorption and re-emission of supernovae flash by interstellar dust. And then this infrared echoes around the Cassiopeia A are observed at a wavelength of 24 millimeters with the help of MIPS aboard the Spitzer Space Telescope. That's it from my side, and these are the references which you can refer after the session. And then I thank each one of them for giving me an opportunity to explain about the supernovae. Now, Kishore is going to explain about the other two supernovae types, supernova type L and supernova type E. I'm done, Sagan, now.
Yeah, okay. So Kishore can start.
Hello, am I audible?
Yeah.
Okay, cool. Okay, now I will be covering the other two types of type 2 supernova, which are type 2L and type 2P. Type 2L is nothing but linear type, and type 2P is plateau type. This type 2L and type 2P are basically distinguished from the light curve analysis, which is nothing but the graph plotted between the luminosity and versus time graph. So, okay, when the spectrum of a type 2 supernova is examined, it normally displays Balmer absorption lines, which is the visible spectrum lines. So, that is reduced flux at the characteristic frequencies where hydrogen atoms absorb energy. So Balmer series, you know, right? From higher energy to principal quantum number of n is equal, that is 2. It actually occurs these Balmer absorption lines. The presence of these hydrogen lines actually distinguishes a type 1 supernova from type 2 supernova. Yesterday, as they discussed. So yeah. So when the luminosity of type 2 supernova is plotted versus time, it shows a characteristic rise to a peak brightness, as you can see in the right side of the graph. Then it is followed by a decline. So these light curves basically have an decay rate of 0.008 magnitudes per day. But this decay rate is much lower when compared to type 1A supernova. So then, depending on, as I mentioned initially, depending on these shapes, they are distinguished into these two types. So for type 2L supernova, it shows a linear decline following the peak brightness. But in the graph, you could see, although it's not very perfectly linear, signs is obviously approximations. So it is, we are considering it as a linear, basically. It's assumed. So by contrast, the light curve of a type 2P supernova has a distinctive flat stretch, as you could see, in the shape of a plateau. So during this decline, so this representing a period where the luminosity decays at a slower rate. So you could see the graph actually. So the type 2 linear, type 2L, where decay rate or the slope of this graph is very much higher compared to type 2, this plateau type. So the decay rate of this linear type is compared to be higher than this plateau type, basic inference. So the net luminosity decay rate is lower at 0.0075 magnitudes per day for type 2P, which is less than type 2L basically, compared to 0.012 magnitudes per day for type 2L. Then the general question might arise: why the shape till peak brightness? If you see the supernova type 2 is not distinguished into P and L, but after peak brightness, if you see, it gets distinguished into two types. So why that difference is happening? All might be thinking. So the answer is no. The difference in the shape of the light curves is believed to be caused in case of type 2L supernovae is by expulsion of most of the hydrogen envelope of the progenitor star. Progenitor star means the star that undergone this supernovae basically. So, but in case of type 2P supernovae, you could see the shape is differing because it doesn't behave like the expulsion of most hydrogen envelope, but it behaves in a different manner, which they call as the plateau phase of this type 2P, which is due to a change in opacity of the exterior layer. So regarding this plateau phase, I'll be now in some time I'll be explaining detailing. So you could see that in type 2 linear supernovae, the decay rate is actually maximum. So why it is maximum means, because if you see when the mass of the actually it is nothing but the expulsion of hydrogen envelope. So nothing but the mass is actually expelled. So when mass is expelled, automatically energy decreases and the luminosity decreases at a greater rate when compared to this type 2P supernovae, in which actually this expulsion or this mass loss is not like directly like happening as in case of this linear type. So now I told like I'll be explaining in a detailed manner of this type 2P supernovae. Let me explain the plateau phase of this type 2P supernovae. So yeah, the onset of the plateau phase actually corresponds to change in opacity of the opacity in the outer layer of the exploded star. Outer layer, of the exploded star. Outer layer means that envelope I am talking about. Then, as the shock wave core collapse, we know this type 2 supernova is primarily caused because of this core collapse. So when this shock wave is produced by core collapse, it propagates throughout the star. It actually heats the outer envelope of the star to over 1 lakh degree, 1 lakh Kelvin. So this temperature is high enough that the hydrogen envelope of the outer layer gets ionized easily. So there is a general property distinguishing normal hydrogen and ionized hydrogen. That is, ionized hydrogen has a higher opacity compared to normal hydrogen. So if you see the radiation from inner parts of the stars can't escape. Radiation means basically they're talking about the photons generally. So from the core of the star, if you see, the photons could not escape the outer layer. So now you could visualize that this outer layer, now this ionized hydrogen outer layer acts as a mask, preventing us from knowing the data about the core of the particular progenitor star. So we can observe only the photons from the outermost parts of the star. Innermost parts, it's actually blocked by ionized hydrogen. So the diagram down you could see, in left side actually you could see the the core, the photons of the core region could not escape, whereas the outer layer photons actually escapes. So then in right side image, what they are telling is after a few weeks, if you see, the outer parts of the star generally have cooled sufficiently that this ionized hydrogen now is able to recombine to form normal or neutral hydrogen. So now the opacity is actually decreasing, and now it slowly starts increasing in the photon emission, which is nothing but this only actually reflects in the light curve you could see, because you could see after a peak it was decreasing, right? So but you might think after this particular ionized hydrogen that process happens, this luminosity should have been increasing, but it is decreasing. For that reason, now I'll tell, because after a few weeks, if you see the outer parts of star, it has cooled to form neutral hydrogen. Then in core collapse, this supernovae, the critical temperature for hydrogen, that recombination, lies between this 4000 and 6000 Kelvin. So a neutral hydrogen is transparent at most wavelengths, and this recombination front where the so after a certain time, if you see the transition phase is happening at the outer layer actually. So that transition phase which is happening at the outer layer, from that point we will be calling the outer layer as the photosphere of the star, because from that actually now luminosity starts increasing, right? So in this time they will be it is called as the photosphere of the star. So once the hydrogen then starts to recombine, photons from the hotter and inner regions, so it starts slowly escaping, and we are able to see the deeper parts of the stars. So then it doesn't stop. Actually, in type 2 supernovae, if you see, then after this process, we all know this outer layer will be keep on expanding, so that later on it will be forming a nebulae. So this actually this expansion causes the outer layer, that is photosphere, to actually that expansion actually sucks the photosphere inwards, so that the luminosity actually starts decreasing. That only here they are told, like the type 2 supernovae, the position of photosphere corresponds to where hydrogen recombination is taking place. So since the temperature of recombination is constant, the supernova expands and cools. Then the photosphere recedes into the star. because of that expansion, and a plateau. The plateau is generally called the length, which is dependent on the depth of how much depth of hydrogen envelope is there. That is the region of the plateau actually. It's created in the light curve. So when the star continues to expand, the it actually forces the photosphere deeper and deeper into the star, so that in a process, it actually simultaneously the successive regions cool to the temperature of recombination. So this temperature actually remains essentially constant as the photosphere recedes through the hydrogen envelope, and so a plateau is created in the light curve. So general idea is that after that ionization phase happens, it actually starts decreasing, and then actually it some luminosity should have been increased, but this expansion of the star system actually dominates, so that it actually sucks the photosphere, and so that the luminosity then keeps on further decreasing. It's the basic idea behind this plateau phase of the type 2 P supernovae. So only I thought like this much detail about the supernova is not sufficient, so I thought of explaining in a more deeper manner through a case study from a book actually. Bro, actually in the top tab I have that book, but this black screen is actually like hiding. How should I take off that? Anyone? These options are like hiding the tabs so that I couldn't open the book. So what can I do?
Oh, you can move that floating.
Oh, okay. Yeah. I got it. So yeah, now let's see two case studies of each one of supernovae type 2, like P phase and P, and next following I'll be talking about supernovae that type 2 L. So yeah, actually I'm covering only the summary part, because it's actually a huge lesson, and it comprises of 25 pages. I could not cover within this time because of time constraint. So I'm covering only summary part. So yeah, let's move. Supernovae type 2P are the most common supernovae in the contemporary universe. What does this mean? Means like um, the probability for the occurrence of type 2 P supernovae is greater than 50% compared to other types of the type 2 supernovae, basically. So they occur in young populations, and their progenitors are red supergiants. So the stars having Zam's mass means nothing but the main sequence stars mass, basically, because from that stage actually nuclear fusion starts, and we are concerned after that stages only. So stars having the Zam's mass, its full form is zero aging main sequence stars. So its masses in the range of about 10 to 30 solar masses are expected to be red supergiants when their cores collapse. This is a general definition we are learning till now, but the experimental technique, which is archival imaging, so it suggests a lack of type 2P progenitors that are greater than 16 solar masses. So here you could see, according to definition, 10 to 30 solar masses are expected to undergo this type of supernovae, but here there comes an through experimental data there is a discrepancy which states that greater than like 16 solar masses of these cores doesn't like it is lacking. So yeah, so this problem is basically called a famous one which is known as red supergiant problem. You could get more info by searching it in internet. Many data are available. So yeah, next, the hydrodynamical modeling and light curve fitting tends to suggest the opposite, which is an excess of high mass progenitors. In experimental data, even you could see there are so many like the different techniques actually yielding different sorts of results. Both are actually totally opposite. You could see an excess of high mass progenitors here, masses in range of less than 16 solar masses. So yeah, other evidence hints that the truth may be between these two extremes. So it is not yet clear whether this type 2 P are all due to collapse of ion cores or due to electron capture in the lower end of the core collapse mass range. What this electron capture collapse means, I will show somewhat in a detail, in a brief manner. So in this diagram, you could see when fusion starts, it starts from helium, then hydrogen, then it keeps on moving. So when it reaches the neon phase, actually, so this neon has a capability of like capturing every electrons, so that it forms like ultimately a neutron star, and this type of collapse is totally like different from the like core collapse, as you could see. So yeah, because the initial data we saw like it suggested about 10 to 16 solar masses, or can be like this red supergiants. So in that range only you could see 8 to 10 solar masses only actually neutron stars also form. So this electron capture collapse is basically the neon core actually capturing not only neon, like oxygen plus neon and magnesium, that the combination core actually capturing electrons and producing a collapse actually, which is the electron capture collapse actually. So then we could see although shock breakout. Shock breakout means shock breakout means in core collapse you could see like when in an initial stage of like supernova, shock is propagated from the core to the outer layer. So during that region, a flat host like wavelength is very short and very small. It becomes very difficult to like experimentally capture it. So it is the shock breakout actually from an type 2 P supernova has not yet been observed. The early post, the early post breakout fireball phase has been. The fireball phase means like from that main sequence till what we are that supernova is there, that particular star actually it's the fireball phase. So the prospects are good that breakout will be observed at both high and low and high redshift, providing the constraint on like progenitor radii, then explosion energies, as well as this provides an like opportunity to study like the shock non-equilibrium shock physics. So by studying from this para, I understood like by studying about the shock physics or the shocks in a more deeper manner, we could get the answers to some this yesterday one question was posed, right? So sir was asking like why how higher elements are like producing. So might be this also might be the key, I guess. So yeah, let's move. So then when core collapse occurs in a red supergiant, the massive hydrogen envelope yields the characteristic plateau in the light curve as a recombination front sweeps inward in mass due to the expansion of the ejecta. This is nothing but saying that the plateau phase of that supernova. So the models of light curves and spectra depend on the parameters such as progenitor radius, then explosion energy and ejected mass, as also the nickel content and its mixing. Nickel content because when supernova is initially at the initial stage of an explosion, that the first element we know till iron only by fusion actually happens, then collapse happens. So it will be when it ejects out, first this nickel content will be more. So I think they are analyzing this nickel, but this I'm not sure. So thus observations can constrain these parameters. So most calculated pre-genita models are non-rotating and non-magnetic, approximates to only approximations to reality. The light curve and spectral synthesis modeling requires such models to be mixed by hand. Then in reality, the mixing may be on small scales as expected from Rayleigh-Taylor and other hydrodynamic instabilities. So actually, truly I should say this para while reading, I didn't get, because this is some sort of mathematical analysis they are doing with the graphs they are obtaining, that is light curve and spectral synthesis. So I'm not sure. So I will skip that para and move to next para. So some supernovae type 2P are weak. They are dimmer than typical supernovae type 2P with lower ejection velocities and with less ejected nickel content. The origin of these events, although still it remains uncertain actually. So, but the early suggestions say that it also might be, it might represent the formation of black holes, but there is no proper evidence for this. So this collapse may be initiated by electron capture, that only in degenerate oxygen neon magnesium cores. But other evidence suggests that no supernovae type 2P arises from a degenerate core. So as the ejecta expand, the envelope recombines and becomes optically thin. So in this actually, that ionized phase is changing to normal hydrogen, I guess. So when the recombination wave reaches the base of envelope, the luminosity declines steeply by several magnitudes before eventually beginning a slower decline, followed in most cases by the radioactive decay of cobalt. So nebular phase spectra yield information, nebular phase actually, that its spectra actually yield information on the structure and composition of the inner core. Optical and infrared spectra can be used to explore the masses of individual ejected elements, which together with the evolutionary models lead to estimation of that zero age main sequence mass of the ultimate mass of the progenitor basically. So the type 2P show various signs of circumstellar interaction, although not as strongly as type 2 narrow. There also is ample evidence for dust associated with this type 2P, some pre-existing the supernova and some formed after supernova in CDS or D and or deeper in the ejecta. What is the full form of the CDS also? I'm not sure. Might be circum, but I'm not sure. Next, the case study of type 2 L, I'm interested to talk about. So here also, like before said, only summary part I'm covering. So in type 2 L, it comprises an interesting subclass of supernova type 2. But the lines between the supernova type 2P N and supernova type 2L are blurred. So in this, they are telling we could not distinguish very clearly the different types of these supernovas actually. So type 2L may represent the low end of the distribution of pre-supernova envelope mass, and plateau behavior rather than a distinctly separate class of explosions from supernova type 2p. But the envelope mass can that it cannot be so low that the result will be an type 2 B type. So type 2 B type is the most like in terms of energy, like it is the weakest I gone through actually. So there is ample evidence in the narrow emission lines and the late time flattening of light curves that circumstellar interaction is important, and hence that it is difficult to cleanly discriminate uh, type 2L from type 2N. So there is a strong like suggestion that the pre supernova envelope mass and circumstellar interaction effects are related. The scarcity of envelope mass accounts for the presence of the circumstellar matter as matter ejected prior to explosion. Type 2L can show substantial luminosity a decade or more after explosion, which is actually an evidence of continued circumstellar interaction. Circumstellar interaction means like around the boundary of the star, whatever like matter is present, with that like of interactions happening, which produces variety of radiations. That is like termed as the circumstellar interaction. Interstellar means like between two stars. Circumstellar means like around a particular star actually. So on the other hand, it is not clear that it accounts for all the mass of the original main sequence progenitor, nor how this qualitative aspect is different from that for type 2N. So from this, they are telling like from the mass of based on the mass of the main sequence progenitor also, and with the help of the like qualitatively also, like we could not differentiate type 2N from this type 2L. So yeah, the outstanding issues then are then which stars eject sufficient mass to produce type 2L rather than type 2P, and the mechanism of that mass ejection. Some of the issues they are mentioning. So yeah, complementary issues are what distinguishes the circumstellar matter in type 2L from that of type 2N. So some supernova type 2N do show phases near decline, and in some others the greater flux from the circumstellar interaction may mask early rapid declines characteristic of type 2L. So from this last three lines, you could see that it is somewhat the type 2N is behaving somewhat like similar to the type 2 L, because there also we saw a linear decline was there, but here also it is like type 2N is also like showing sort of linear decline. So how to differentiate this type 2L and N based on light curves? They are not sure, I'm thinking. Then some type 2L show spectral evolution rather similar to type 2P, but others have differences. Some show narrow P Cygni profiles, which is indicative of a slowly expanding circumstellar matter. P Cygni profiles means they are the spectrum of blue shifted mostly. So blue shifted means it actually signifies less expansion and more contraction because it's blue shifted. So yeah, some type 2L have typical nebular spectra of core collapse events, but others lack the characteristic magnesium, oxygen, calcium 2 spectral lines. Notion that type 2L represent a distinct range of progenitor masses has been suggested but remains unclear. Because for type 2p also we saw there were like certain anomalies. I think similarly for type 2l also, like distinct range by definition we are defining, but still how it is we didn't like the data is like unclear that trying to say like. So although the mass of the hydrogen appears to be low in type 2l, there is evidence that progenitors are red or perhaps yellow supergiants. So the exams masses of the type 2l progenitors may be around 20 solar masses, but again the data is sparse. Future observations of this supernova type 2l should seek to determine the exams mass from observations of the progenitor and perhaps from measurements of the ejected oxygen abundance. Pre-maximum data including photometry on the rise would be valuable. Then yearly spectra to characterize the narrow emission lines, and the evolution would help to establish whether the circumstellar matter extends down to the photosphere of the progenitor and or is inertial. Spectra in these both of these photospheric and nebular phases should be examined for evidence of like asymmetry happening. There is also no like published spectropolarimetry on this particular type. Evidence of again the evidence of shock breakout and compact and for remnants is also not yet available. So since the implied loss of envelope from the progenitor suggests that the remaining star is more exposed than for type 2p, near infrared spectra might provide evidence of enrichment in helium and other elements. Because we saw like initially from that light curve, type 2l actually the decay rate was very much higher, and they suggested the particular reason for that was hydrogen was like stripped off. So yeah, so they are telling like there might be evidence of the higher elements after hydrogen, that is helium and other elements. So yeah, now Meghna will be continuing the further topics. Thank you. How? Okay.
Am I audible?
Yeah, you're audible.
Okay. So I'll be talking about the neutrinos produced by type 2 supernovae. The supernovae are considered to be the strongest and most frequent source of cosmic neutrinos in the mega electron volt energy range. And one of the means to get direct and immediate information about the inner workings of the supernova is from the observation of neutrinos emitted during the formation of neutron stars. This is one of the main processes that produce electron neutrinos in type 2 supernovas. In high density conditions, the electrons and protons interact through a W boson and form electron neutrinos and neutrons. Okay, so neutrino-driven mechanisms in supernovas. Within seconds after the infall, the core collapse supernova radiates a vast majority of its binding energy, about 99% of its binding energy, in the form of neutrinos of all flavors. And this happens in a very small span of 10 seconds. This high energy burst of neutrinos transfer most of its energy to the surrounding materials, and these outer layers get blown off, and this matter outflow is termed as neutrino-driven wind. This makes them an interesting site for nucleosynthesis of ion group elements and trans-ion nuclei, basically all the heavier elements that are found on Earth and within us, which reminds me of what Carl Sagan said, we are made of stardust. Yeah, some research papers also say that this neutrino burst from the collapse may transfer enough energy to the shock front to keep it from falling back into the core. Okay, so now I'll be telling about this specific supernova SN 1987A, and soon I'll tell you why it's special. In 1987, a Type II supernova was observed in the Large Magellanic Cloud, which is at a distance of 60 kiloparsecs. Luckily, at the time, there were two underground neutrino detectors that were taking data, the Super Kamiokande and IMB. There was another on the ground neutrino detector called Baskin. Okay, so these detectors simultaneously observed the neutrino events about 7 hours before the optical supernova was observed. And these observations were consistent with our theoretical models, which, as I mentioned before, which says 99% of the energy is radiated away in the form of neutrinos. So this information from supernovas can help us learn more about neutrinos, like how they change over long distances, or help us set limits to how massive they are, about their charge, flavor, and other properties. And the other way around, neutrinos can also help us understand about supernovas, like more about the core collapse, the explosion mechanism, and the formation of neutron stars and black holes. Uh, Further, the neutrinos undergo flavor conversions in the dense medium inside supernovas. So, getting data about this could help us and study neutrino-neutrino interactions. But unfortunately, this event, the SN 1987A, is the only supernova neutrino event detected so far. Our detectors now are working towards getting more data on supernova neutrino events. So this was the data from 1987. Um, so theoretically, it is predicted that a supernova in our galaxy could result in about 5,000 to 8,000 neutrino events in a single detector. But as you can see here, the Kamiokande detected 12 antineutrinos, the IMB detected 8, and Baskin detected 5 antineutrinos. One thing you can note here is that the neutrinos detected by Kamiokande arrived in two distinct pulses. The first pulse with 9 neutrinos and the second one with 3. But to gain more insight about this, we need to um, observe more such neutrino events. Okay, so I'll be ending with by mentioning about the diffuse supernova neutrino background. So the DSNB is a cosmic background which is formed by the accumulation of neutrinos from which were emitted from these core collapse supernovae in the past. Their existence was predicted before the observation of supernova neutrinos, and this can give us information about neutrino emission properties and stellar dynamics. The DSNB signal is expected to be detected soon with our detectors like Dune, Juno, and Super Kamiokande. So that's it from our side. Thank you.
Uh, Yep, thank you. That was a good presentation. If anyone has any questions, I think there are a few questions on chat. You can answer them.
Hey guys, so it's a nice presentation. So as Adish said, we can see the questions in the chat box. So we have one question from Sonal. What is meant by decay rate of light curve? Can anyone answer? Speakers today?
No. Can I answer?
Yeah, Kishore, you can.
That curve, light curve, if you see, decay rate means nothing but I'm telling the slope of that curve basically. It's actually decreasing, right? As time increases, the luminosity gets decreased. So I'm mentioning it as a like rate of change happening. So it is generally I'm mentioning like it like the decay rate of the particular curve, that curve. Is that fine?
Okay. And we have another question from Aryan. If photons can be absorbed more, then why luminosity decreases?
Okay. From my part, I think. Okay. In the plateau phase, from what I understood, after the ionization phase happens, the core actually cools and actually it particularly expands basically. So while expanding, there is a recombination like shock front or recombination front is actually it's pulling the photons towards the center of the core. Simultaneously, also the mass of the particular is actually ejected out. So when if you see the mass is actually mass is nothing but the energy actually. So which ultimately contributes to luminosity. So actually it because of that, as time passes, the luminosity decreases, I guess. But this recombination front actually, when that particular core is actually that it's expanding, the outer layer that is the photosphere is tending to be like pulled inwards actually. I think I answered, but could it be someone could answer it in a better way?
Okay, bro. So we don't have any more questions. So does anyone here have any questions or comments on today's?
Yeah, I have a question.
Yeah, Siddharth.
Yeah, so we say that when the mass of the core is above the Chandrasekhar limit, now above the Oppenheimer limit, then it converts to the black hole. And it's because the neutrons can't hold on the pressure and they all breaks. But why they just go to the singularity? Aren't there the quarks that can hold that pressure? And there is a next stage after which the quarks then they are not able to hold that pressure and then to the singularity. Isn't there this step between all of these?
So like to summarize it, like you are asking like when neutron degeneracy pressure doesn't hold up, they form into singularity and form black hole. And you are asking like there's any transition phase in between or not. Is that it?
Yeah. Is there something like quark degeneracy pressure?
Okay, so we have Vikrant here. I think Vikrant can answer on quark degeneracy pressure. Vikrant?
Hey, am I audible?
Yeah, Vikrant.
Right. So, I'm not an expert on this. I haven't even read about this, but I believe there are quark stars that are possible, but they're highly hypothetical. And like you said, there might be a quark degeneracy pressure. The neutrons, you already know, they are kept apart by degeneracy pressure and so on. But if you consider that, under the level up to the level of quarks, then yeah, there might be possible, right? But they haven't been detected, and they could form like any massive star collapses and everything. And it is possible that beyond a neutron, it may not be heavy enough to form a black hole, is what I remember reading. Right? I mean, when you think about it, you would think that the whole idea of quark degeneracy pressure would come in only if the star was massive enough to compress your neutrons as well, a stage beyond neutron stars. But yeah, it would be more like you'd find these quark stars, if you want to call them that, inside neutron stars. So there'd be like a part inside the neutron stars where they're held from the quark degeneracy. But this is again just a hypothetical thing, and this is all that I know about it so far. So that's all I can tell you right now.
Can there be a quark star inside the black hole?
I am not sure about that, because your black hole is more of a mathematical entity where you have in a layman's term you would have an infinite curvature. So it's a place where your space and time are reversed. So the way that you understand your normal particles, your normal quarks and everything else would probably be different. So I don't think there would be some sort of a quark star inside a black hole, but again, it's just hypothetical. We still don't know what happens inside a black hole. Neither do we know what happens. What are the consequences of a quark star specifically if it's inside a neutron star? If a quark star can exist all by itself, is that possible, or would it be a part inside a neutron star, or it might even be inside a black hole? Who knows? But for that, like I said, you'll have to understand very well what is happening in this singularity. You can't get to singularity. That's the problem. So yeah.
So, but there can be the thing that quark star have enough gravity so that light can't escape, and we can call it a black hole. Not
Yeah,
that.
again, I'm not really sure about that because I haven't read about quark stars recently. So I'm not sure if there's any recent developments that have happened that could answer your question. But I would encourage you to go ahead and read quark stars. I just found there's a Wikipedia page.
Okay.
Okay, and adding to Vikrant's point, there is actually one type of star called as strange star, it seems, where the star is made up of only strange quarks. So there is one research paper also which I just found regarding that. So quark stars are mostly hypothetical, and the quark degeneracy pressure, there is quark degeneracy pressure actually, but when neutron degeneracy pressure is not enough, the neutrons will break and it will form like a quark gluon plasma, it seems. One state of matter called as quark gluon plasma, where the whole star is made of discrete quarks only. Instead of neutrons, there is only quarks. And this quark degeneracy pressure is almost equal to neutron degeneracy pressure, it seems. So there is no quick transition. Rather, in many stars, as soon as degeneracy pressure of neutron is lost, it becomes black hole, because quark degeneracy pressure is almost equal to neutron degeneracy pressure, it seems. So that's why we can't see any star where there is only quark, made of only quark. Rather, it goes off to neutron, like that we can tell.
Okay. Thank you.
Okay, so anyone else have any questions? Okay, Sonal has another question.
Right. I think
Vikrant, we couldn't hear you, bro.
Neutrons.
Your voice is breaking completely. I think you can
Right.
put it in the chat.
Internal structure of the neutron star might be a quark gluon plasma. Yeah, can you hear me now?
You're still breaking.
Okay, but in the meantime, we can answer Sonal's other question. How do we interpret formation of interpret information from a light curve? How can we interpret the information from a light curve? Yeah.
I thought from a book now. In that detailed explanation for light curve, even like how they are interpreting it is given. I will post the book's link. If we could read it, it would be like better. I don't know.
Okay, Kishore. Post it in the chat box.
Hmm.
Okay, Vikrant is saying that I was just saying that there's a possibility of internals of a neutron star to become a quark gluon plasma. Yeah, Vikrant. Yeah. So in the core of a neutron star, the pressure will be so high that the neutrons inside the core will break to form a quark gluon plasma, and it would be a short-lived. And moreover, the strange star, what I told, the star made of strange matter, it is also in the same case. Like when the neutron star core has so much pressure that it decays and forms strange matter and all. It seems. I think I'll post the research paper about the strange star in the chat. Okay. So okay then. Anyone else have any doubt? Okay, I think I can ask the leaders of theory one, like Aruna and Aratha, to tell how was the today's lecture. So Aratha, you're here.
Yeah, bro. Can you hear me?
Yeah, Aratha.
Okay, so I mean, from today's lecture, it was very informative actually. But to be honest, I didn't quite get much of it. I mean, there was too much details, and I think if you are like learning it as a beginner, it might be hard for some people. Like, I mean, the information was good, and you guys studied. And but I want to ask, like, did you had any meeting before, like this current meeting before any meeting trial ones?